Hi guys, welcome back to the last part of this Explainable AI series. Today I want to talk about Layerwise Relevance Propagation, a method which is designed to explain the relevance of an input for a deep neural network. Later in that video I show you how to use the method on an example dataset for brain cancer classification on medical MRI scans. MRI stands for magnetic resonance imaging and looks like the image shown here. You've probably seen it before. We not only want the neural network to tell us if brain cancer can be found on that image, but also why the model thinks so. And for this we will use Layerwise Relevance Propagation. Let's start with an intuitive explanation of what the method does. Layerwise Relevance Propagation, or short LRP, was presented in this paper and has the overall goal to explain the relevance of inputs for a certain prediction. Typically, this is applied on images so that we see which part of the image, or more precisely which pixels, made our model arrive at a certain prediction. LRP is a model-specific method as it is mainly designed for neural networks. Generally, the method assumes that the classifier can be decomposed into several layers of computation. It can also be applied on support vector machines. Let's have a look at this example from the paper. In the forward pass, the image goes through a convolutional neural network. That means several layers of convolution, pooling, and other operations in order to extract the features from the image. Then we pass these extracted features through a classifier, which is typically a fully connected neural network. This gives us the output, so the prediction. Here we have two classes, one for cats and one for no cats. At this point, we are interested in why the model predicts cats, so the red square. Now, LRP goes in reverse order over the layers we have visited in the forward pass and calculates the relevance scores for each of the neurons in each of the layers. When we arrive at the input again, we can calculate the relevance for the individual pixels. Positive relevance scores would indicate that the pixels were relevant for the prediction, and negative values that these pixels would speak against it. This leads to the heat map we can see on the right side. This process is in the paper also called pixel-wise decomposition. The visualization we see can be extremely helpful for many areas, such as in medical imaging, because often the humans require an explanation why the algorithm spits out a certain prediction. We will see more of this in a few minutes. Now that we are familiar with the basic concept, let's have a look at how we can calculate these relevance scores. Let's assume we have this cat image that we pass through this CNN to get a vector of extracted features. This vector is further passed through a multi-layer perceptron to get the prediction for our input, so in this case cat. That's how the basic architecture of our model could look like. To better understand LRP, let's go over an example. The intuition is that we want to calculate the relevance layer by layer until we get the values for each individual pixel. We begin with the output neuron of our model and assign it the function value as relevance score. In a classification problem, we would for instance have 80% cat, so we choose the corresponding neuron and 0.8 as value. We don't care about the probabilities for the other classes and therefore set them to 0. Let's focus on the classifier part of our network. Here we have 4 layers, and we can denote the relevance for the output neuron with R1 because it's the first neuron, to the power of 4 because we are in layer 4 of the classifier part. Now we can move to the next layer. The relevance of a neuron is calculated according to this formula. It gives us the relevance R for a neuron I in layer L. So our current layer L is the third layer, and the output layer becomes L plus 1, so the fourth layer. The calculation for neuron I now works as follows. For each neuron J in the layer L plus 1, in this case we have only one neuron, we calculate the activation based on the neuron I compared to all neurons in the layer. The activation is calculated according to this set ij on the right side. It's simply multiplying the input for the neuron I in our current layer with the weight that goes into the neuron J in the next layer. This input x comes from passing the pixel values through the previous layers. This tells us how strong the activation between these neurons is. Intuitively, if there is a high value, it means that the neuron was very important for the output. So we interpret this fraction as a relative activation of a specific neuron compared to all activations in that layer. Finally, we multiply the relevance score of the neuron in the next layer with this relative number to propagate the relevance one layer backwards. Doing so, we get the new relevance scores for the neurons like visualized here. The intensity of the colors indicates the relevance of the neurons. When we move to the next layer, we do the same procedure. Here we have several neurons in layer L+1 now, which is layer 3. The sum over j means we calculate the relevance activation of a neuron for each of the neurons in the next layer and multiply it with their corresponding relevance score. And again, we get the relevances for each of the neurons in layer 2. Note that the sum of the relevance values stays the same for each layer. In this case, the relevances will always sum up to 0.8. Of course, this approach is not limited to dense layers. We can also apply it on convolutional layers. That's why we can further propagate the relevances through the network until we get a specific value for each pixel in the input image. This image also nicely summarizes the idea of Layerwise Relevance Propagation. Neurons that lead to higher activations have stronger relevance flows than neurons that were not important for the prediction. Before we jump into the code, I want to point out that the formula I just showed is the basic variant of LRP, which is also called LRP0. Depending on the layers, there are small extensions of this formula that make the flow of the relevances more robust, but we will see this in a second. Okay, so now we can have a look at how the method works in practice. I downloaded a brain MRI dataset from Kaggle on which we will apply this method. All the code is pushed to GitHub, you find the link in the video description. The goal for the dataset is to not only get predictions if there's potential cancer tissue on the MRI scan, but we also want to know which neurons were important for that specific prediction, such as shown here. Alright, here we are in VS Code. I'll quickly show you the data set. I've put it into data brain MRI. The link to it is stored in that README here. You need to download the data by yourself if you want to use it, because I won't push it to GitHub as it's pretty big. So there is a testing folder and a training folder. And in the testing folder again, also in the training folder, we have 4 additional folders. Those contain the images. So the no tumor folder, for instance, has the JPEG images that look like this, for example. Also from the side. And in the other folders, we have patients that have a tumor. As you can see here, you can clearly see it. Some of the images are duplicates. I don't know why, but I didn't further look into this. So these are the images we will work with. And now let's have a look at how we use them. So first of all, I built a model using PyTorch. And on my local machine here, I have a GPU set up. And this will print true if the GPU is available in PyTorch to speed up the training. So then we can load the data set from this brain MRI testing and training, and we can have a look at some of the images, but actually I just already showed them to you, so we can skip that. And I will go quickly over these sections to focus on the LRP stuff itself. Then we build a model. I use a pre-trained model here, in this case the VGG16. So we can quickly have a look at the architecture. If I print the model itself, it will print the summary. All I do here is adjust the final output layer, so the final linear layer of the model, to output 4 classes, as we have no cancer and the 3 tumor types, and we don't want the 1000 classes from ImageNet. And yeah, this model is automatically downloaded, so it was downloaded right now, I think. And the architecture looks like this. So we have several convolutional layers, as you can see here. And then we have this pooling layer and then a couple of linear output layers, just like I've shown on the slides previously. It's basically the same architecture. One thing I want to point out here is that layer-wise relevance propagation can be quite tedious if you have more complex architectures. Here, as you can see, it's pretty simple. It's just a sequential set of layers. If you have more complex things like ResNets, where you have splits, like different branches of layers, propagating that will not be so easy as we do it in this example, because here we just can iterate over the layers and don't have to care about branches or forks in our network. All right, and then I put this CNN model to the GPU, and then I prepare the train and test data set again, but do some additional transformations like resizing it, and then I create two data loaders, one for the test data, one for the train data, and give them a batch size of 32. That means they will load 32 images for each batch we want to train on. By the way, the data is automatically loaded using that image folder. So as you can see in this description, this image folder expects the different class types, so the different labels, to be in different folders, and then we can simply build a data set using that function. So that's pretty convenient for the folder structure we have. All right, and then we can already train. So as always for classification problems, we use the cross entropy loss, basic atom optimizer. We only need to optimize the final part of the network, actually, because it's a pre-trained network, so most of the things should be fine already. That's why I only need to train 10 epochs, and I run that, and meanwhile, yeah, I think I'll just cut the video. All right, now that training has finished, we have a pretty small loss. I didn't check for overfitting, probably it overfitted a little bit. To better investigate, let's have a look at the test data. So we use our test loader, get the first batch, so the first 32 images, and all I do here is pass them through the model. So here we pass it and compare the labels to the output, so basically calculate the accuracy for that specific batch. So for the first batch we have an accuracy of 65. If we run it again for another batch, we have 81 and so on. Again, this is not super precise, but here we now want to focus on this LRP implementation. And by the way, the classes we see here are the numeric labels of our classes. So we had 4 classes, and that would be this third one, so 0, 1, 2. Yeah. Okay, now let's have a look at this implementation. So I got this implementation, or the inspiration, I did some slight adjustments from those two. So there's one GitLab from a university in Berlin, and then there is this paper, and those describe quite nicely how you can implement it in PyTorch. So let's maybe first jump to the function call. So we call the function here, this apply LRP on VGG16, and we pass our model. So this function only works for the VGG16, and we select a specific input image. So this is a local explainability technique because we can only explain individual images, because we cannot explain the full model, but we can say for this specific image, that section of the pixels was most important. So now let's have a look at what happens in that function. So this is the function where we apply LRP on the model. That's why we get the model and the image as input. The first thing we need to do is add the batch dimension again, because remember, our inputs had a shape like that. And yeah, I've printed this already here. So the image has now a shape like this, but our model expects 4 dimensions. That's why we need to add a 1 here, essentially. So we have 1 batch with 1 image. Then in the first step, we need to extract the layers from our model. And remember, our model looked like this. It's model, sorry. And we have 3 sections here. We have the features section, which is basically a CNN. Then we have the average pooling, which is the connection between the CNN and the classifier, and then we have the classifier. So those are the three sections, and these are the sections we extract here. First of all, we need to treat each of the layers individually, because, for example, a convolutional layer cannot be, so the propagation we apply there is different than on a linear layer or on a ReLU and so on. And that's why I get here the indices for the layers that are linear in our model. So if we run this, okay, it's not defined, 1 second. So if we run this on our model, we get those 3 layers that tell us, okay, at that position, so index of our layers, we have linear layers. Now the next step is we create a placeholder for the activations. So we have all the layers now stored in that list here. We know the list has a length of, let's say, 40. We can also quickly print this. Okay, all of the functions are not defined right now. I think I run this, maybe. Then let's do it again. Okay. And now we can say length of L. Okay, so we have 39 layers in our VGG16, and we create a placeholder now for the activations in each of the layers. That's why we basically create a list where the first entry is the image and all of the other entries are none. So that's what's happening in that line. And then we iterate over the layers, and so as it says here, propagate image through layers and store activations. So that's what we want to do here. We want to go over each of the layers and store the activation of that specific layer in that list. So this is happening here. And maybe one thing, so you might have seen this function here, dense to conv. All of the linear layers are converted to convolutional layers so that we can treat all of the layers the same way. And how do you convert a linear layer to convolutional layer? Let's have a look at this function. Basically, all we need to do is reshape the weights so that they have a like convolutional matrix style shape, like kernel shape. And so basically it's just realigning the weights. And that's why I also had to distinguish between the different layers here. And I use this here, and if we pass this specific layer, I need to reshape the data we pass in. Okay. Now we say if the thing is instance of average pooling, we flatten, because then we have this transition from the feature extraction part to the classifier part. All right, and then we have all the activations inside of that list. Then the next thing is we want to specify the relevance of our last layer. And to do so, we need to basically get the maximum activation in the last layer. So this is the last layer. And then we say, okay, we select the value if the value equals the max. Otherwise, we put a 0 there. So this will give us some sort of one-hot encoding on the output. Because we said we only are interested in the explanations for a specific class and zero out all of the other activations of our output layer. Okay, now what we do is we backpropagate the relevance scores. So now we have the relevances in our final layer already, which is coming from this float tensor here. So we have this one hot output. You can think of it like something like that. So we have 0, 0, 5.5, 0. So we have zeros only the class that we predict is non-zero. And that will be the relevance value for our output layer. For the other layers, we do the same thing like for the activations previously. We set none for each of the relevances, but now in reverse order. So all of them are none except of the last one. Here we had the The first one was the image and the others were none in the forward pass. Now we backpropagate the relevances. And now what we do is we iterate over the layers in reverse order. So this thing here makes sure that we iterate in reverse. So for example, if we have a range of 10 and print that, looks like this. So that, for example, like this, that gives us the reverse order of our content. Okay, and what we do here now is we say, if we have a max pooling layer, we replace it by the average pooling layer. That's also mentioned in the paper. You can do that to propagate the relevances. And then we check if we have a convolutional layer or an average pooling layer or linear, we calculate the relevances for that specific layer. Otherwise, we just pass the relevances one layer further. For example, if we go through layers that don't really have weights, so no real activations like ReLU or dropouts and so on. So, and now that section in the middle is calculating the relevances. It might look a bit complex at first, but I'll quickly show you that paper. So in this paper, which is called like this, Layerwise Relevance Propagation and Overview, there is a section called Implementing LRP Efficiently. And they even state how to do that in PyTorch. And basically they say this is the basic formula. And they also mention the other formulas I previously talked about. So the basic rule is LRP 0. Then there's LRP epsilon and LRP gamma. And each of them are usually used in different layers. So for example, the epsilon rule adds in the denominator a term epsilon, which is not present here. And the gamma rule adds to the weights an additional transformation. So basically it's increasing the weights. For example, they also say another enhancement which we introduce here is favoring the effect of positive contributions over negative. So all the positive values will be increased to get better relevances for these values. And regarding the layers, there's also a section called which LRP rule for which layer. And here they state upper layers LRP 0, middle layers LRP epsilon, lower layers LRP gamma. And that's exactly what we do in this code. So we say if the layer is smaller than 16, we apply the lower layer rule, so the gamma rule. Then here in the middle layers the epsilon rule, and in the upper layers the 0 rule. And that, so for that, I've copied this from the codes which I linked here. And basically we define a couple of lambda functions. So that means when we call that function, for example, here it is, depending on, so that function is passed to new layer, which is a function defined here. And that function now uses this row as g and has as argument all of the weights of that layer. And we set, for example, let's go to the paper one more time. For the weights, we apply in the gamma rule a transformation like here. And now the specific value we want to apply here is depending on which rule. And here you can see we say that lambda function simply returns the same value. So for the non-gamma layers, we essentially apply no transformation. And for the gamma layers, we apply that transformation, which says we increase the weights by 0.25, all of the positive weights. And the same happens for the epsilon rule. Here we add this epsilon term like it's done here. And then let's go to the paper one last time. Here it says the computation of this propagation formula can be decomposed in 4 steps. And if you look at those 4 steps, so that section here is exactly in the denominator. So we first calculate the denominator, and that's simply by doing a forward pass on the data, on the activations. Then we calculate this fraction. And if you look at this, this term is this term, and that term is that what we calculated in the previous step. So essentially is a fraction between that one and that one. And that can be seen as flipping this numerator with that term here. So it's basically swapping those two, and then we calculate that fraction. This is happening here. And then regarding that part, this is happening in that calculation. And they also state that the third step, so that section here, can be also expressed as the gradients. And that's exactly what we will do in the code. So here are the 4 steps. In the first one, we simply calculate this forward pass, then we calculate that fraction, then we do the gradient calculation, and then in the final step, we multiply it to get the relevances of that specific layer. And that's how the function works. So again, if you want more explanations about this, check out those 2 links. But that basically summarizes the basic idea. Alright, so now we are set to use the function. So we call the function, we pass the model and a specific input image. So at a specific index. Here it's 0. And then what we also need to do, so let's have a look at input shape. The shape is like that, so the channel is at the 2nd position. And typically when using libraries like Matplotlib, you need to put it at the last position, and that's what's happening with this permute function. And then we, in the final step, normalize the relevances to be between 0 and 1. If this image is classified correctly, we visualize why that prediction was made by the model. So let's have a look at the first data point. So here we can see we have a prediction for this specific tumor type, and we see that area clearly spits out, so we have high relevances for that area, and all the other areas are less relevant. So let's have a look at another data point. Here we see it's the same for that. Okay, these images are pretty clear, I would say. Let's have a look at another one. So here it says no tumor, and in contrast to those 2, we see there's no clear section that is highlighted. And so that's actually exactly what we want. Same here. It might be that those points were confusing for the model. That's why they're highlighted here. So here it's the same again. You see, it kind of works as we expect it to work. We visualize the sections that are relevant. Alright, that was my little Explainable AI series. I had a lot of fun going over the different topics, and I hope that you found it helpful or interesting. The code is uploaded on GitHub, and I appreciate any kind of feedback. Thank you for watching.